Dear students, we have learned the binary notation in the previous modules, and with the use of binary notation, we could be able to represent numeric values. However, actually, the binary notation is the basis for storing numeric values, but that notation is a little bit changed in one form that is known as 2's complement notation to actually represent the numbers. As you might remember that when we learned the binary notation, we were only discussing about the positive numbers. So we can represent, for example, 5 with the binary notation 101, and if it is 8 bits, you can add 5 zeros. But what if there is -5? So how we will represent -5 in using binary notation? So here is the scheme using 2's complement, which will give us the leverage and which is actually being used by the today's computers to represent the numeric values, both positive and negative. In today's computers use fixed number of bits to represent each value, and normally they use 32 bits. However, to demonstrate 32 bits in this module would be very difficult, and we will be discussing smaller example for demonstration purposes. So let's see one example using 3-bit pattern. So you can see we have written 3 bits in a way that 0, 1, 2, 3, then 4, 5, 6, 7. So you might remember that this was decimal 0, 1, 2, 3, and then 4, 5, 6, and 7. And we are saying that from 0 to 3, this will represent positive numbers 0, 1, 2, 3. And from 4 to 7, this will represent -4, -3, -2, and -1. So the rule is for positive integers starting from 0, going upward until a single 0 is reached, followed by all ones. So we have reached to a position where only 1 0 and all ones. And for negative numbers starting from 1, going downward until we have only 1 1 followed by all zeros. So if we see it in the 4-bit pattern, we have something like this. So from 0 to 7, we will represent the same way as we were displaying in the decimal and binary notation previously. But 1111, which is actually 15 in decimal, but it will represent the value of -1 using 4 bits. And similarly, I was telling you that computer use 32 bits. So how to convert from positive to negative representation? So here is a shortcut way. So for example, you want to see that if 7 is represented with 0, 1, 1, 1, so -7 would be represented by what bit pattern? So you start from right side until first one is reached. So we have reached first one immediately, and after that all of the ones are changed to 0 and 0 is changed to 1. So this will form 1 0 0 1, which is representing -1. So let's see another example. So let's see, we want to now say, for example, 6. So 6 has 0, 1, 1, 0. So -6 will be represented by what bit pattern? So as I already said, let's start from right side. Copy all of the bits until first one is reached. So 0, this 0 would be reproduced as it is. First one is reached, that would be written, and after this first one all of the things will be changed. 1 would be changed to 0 and 0 would be changed to 1. So this will become 1 0 1 0. So you can see minus 6 is represented with 1 0 1 0. Similarly, you can go from negative to positive as well. So now addition in 2's complement, that is same as we have discussed binary addition. So for example, we have used 3 plus 2. So you can see 1 1 1 is 0 1 1. So this is the combination of 5. That is awesome. What about minus 3 and minus 2? So this is giving you minus 5. As you can see that it is at bit pattern of 1 0 1 1. So you can see on the previous slide that 1 0 1 1 is representing minus 5, and then 7 plus minus 5, that is giving you 2. That is perfect. So all rules are same except that all bit pattern including the answer are the same length. So truncation is performed. So if you find, for example, when you add minus 3 and minus 2, you might have noticed that this was 1, this was 1, 1 1 is 0, 1 carry here, and these are 3 ones, so it will become 1 1. So this 1 will be truncated. So you will leave this one from your bit pattern and you will remain within the 4 bits if you are using 4-bit pattern. If you are using 3-bit pattern, you will remain in the 3-bit. If you are using 32-bit pattern, you will remain into the 32-bit pattern. So any bit that is exceeding from the bit pattern which you are using, that should be truncated. And then there is another problem of overflow. So for example, using 4-bit pattern, we know that positive number we can represent 7 and negative number we can represent minus 8. So if we want to add 5 plus 4, that will become 9. But 9 cannot be represented in 4-bit pattern. So that is known as problem of overflow. And I also want to let you know one more thing, that you can also see that the most significant bit, if it is 0, it is representing positive numbers, and if it is 1, it is representing negative numbers. So today's computer have longer bit pattern, normally 32. So maximum positive values which we can represent is this one. And if still overflow occurs, you know that truncation is not a problem. You can just leave that bit. But if there is an overflow, then you can use more bits, or you can change the units, like calculating things in kilometer rather than meters will give you less number of bits. And then I want to share a story of dangers of using computer, that previously 16-bit computers were being used using 2's complement notation to store the numbers, and maximum number that can be represented was, the positive number was 32,768. And on September 19, 1989, hospital system malfunctioned, as 32,768 days has been already passed after January 1, 1900, and thus it produced negative date onto the computer system. So then they changed 16-bit to 32 bits. So if we conclude today's module, we have learned 2's complement, its representation, and how can we convert from positive to negative by coming from right side. And then we already learned about the additions in 2's complement, and we learned about truncation error and overflow errors.